Thanks everyone for joining us. We'll be talking about platform integrity attestation at scale. My name is Jeff Anderson, my colleague is Jonathan Cook. To frame this discussion, first we'll talk a little bit about some guidance that NIST gave a few years back about platform resiliency. Protection, detection, and recovery. Protection, making sure that things remain in a state of integrity. You can think of this as secure boot. Don't boot things that are not what they should be. Detection, being able to detect when things have gone awry. And recovery, if things have gone out of whack, how to get it back into a state of integrity. We will be focusing on detection on this talk, how to integrate detection into a fleet of machines that is quite large and quite complex. So a few topics that will be brought up is policy making, how to describe the intended state of the machine. Routing, how to get signals from the entities that are producing them, the roots of trust, to the entities that will consume them, the verifiers. And reaction, how to respond if the signals don't match what the expectations are. To give a bit of color and context into where we come from, with this, Google has had a bit of experience in wrangling with roots of trust and attestation. We created Titan as a security microprocessor, and we integrated it into our roots of trust, into our machines. This here, it'll do that. This is a dead board with a Titan M2. A variant of this showed up in the Pixel 6 phones that just launched. Now, in our machines, they started out being integrated somewhat like a TPM in that they sit at a low level of the boot stack. They can accumulate measurements and attest to them. There's some fancy active component in there so we can actually measure the firmware before it actually runs on the main processor. A couple of strong assumptions here, though, is that there is a one-to-one relationship between the platform and the root of trust. It is the root of trust for the platform, and it knows all about what measurements matter on that platform. A linear boot stack, very easy to reason about, but does not really track with reality. We now are building machines that are a bit more complex. We now have accelerator trays, NICs, each with their own roots of trust, each with their own parallel boot stacks, and their own roots. So no longer is there one single component that knows everything about the state of the machine. The complexity gets even more hard to reason about and manage when we talk about the machines we would like to build in the future. Multiple power domains, multiple BMCs, base order management controllers, dozens of roots of trust scattered throughout the system. The complexity is starting to get a bit daunting. So we talked, in the title of this talk is attestation at scale. So the scale means we have a lot of machines, and those machines are getting more and more complex. So two different dimensions of scale that we must reason about here. So the scope of this talk, what we'll be sharing, is some design constraints which factored into how we approach this problem and the solution we ended up building. If these design constraints sound familiar to you, our solution might be of interest. We will be sharing what we actually came up with, the middleware to attest these complex machines, and then some standards gaps, things that we had to make up ourselves to get it to tick, and things that we think there should be broad agreement on how to do these certain things. Now, just to be careful with our claims, we are not claiming that what we're sharing today, the approach, is the one and only way to do attestation. There are lots of ways to slice this. This is one of them. We're also not claiming that we have years and years of experience battle-hardened testing of this system. There's going to be evolution as we roll this out and deploy it. We'll learn, we'll make changes, and when what we learn, we'll come back and share. So, some design constraints, some fleet management philosophy from Google. Hard-won lessons. Production in a constant state of flux. There's always, the fleet is never standing still. You have machines, software rolling out, rolling back, machines breaking and getting fixed. Nothing's perfect. Sometimes you'll roll out some software, and for the vast majority of machines it'll take, but then for a few, it doesn't. It doesn't take very long. And that is not a sign that someone is attacking your fleet and messing with your infrastructure. That is a sign that we live in a mortal world and stuff goes wrong. You have to be cognizant of that. Machines are cattle, not pets. We have so many machines that it doesn't make sense to to weep when individual machines die. They're allowed to die. We do like to know what killed them so that we know that it's not something that will affect many more machines, but this is just a fact of life. And because there's so many machines, we need to automate as much as we can. Any solution which requires manual intervention of machines at this scale does not make sense. And finally, we need to reduce the risk of outages. So anything which might cause machines to misbehave or, in the worst case, brick at scale must be avoided at all costs. And to that point, one source of problems at scale is complexity. So we like to keep things as simple as possible, but where we need to add complexity to a system to solve a problem, and we have a choice, it would be better to add that complexity to the control plane where it can be centrally managed, and not to distribute that complexity to the fleet, where it's when it's harder to manage. So here's a rough not-to-scale diagram of our machine fleet, and a few things that will of interest are the job schedulers, the serving machines, and the automation. So the serving machines, the big blue bubble, that is basically our workhorse. That's what runs Gmail, YouTube, cloud. The vast majority of machines are in that bubble. They get their marching orders from the job schedulers, which are highly available clusters of machines which send jobs out to machines as they come in. And then machine automation is how we roll out software to our fleet. So, hey, there's a new update, please take it, making sure that we're not updating too much of the fleet at once. A lot of engineering goes into all these systems. So the property we would like to get out of our system is that jobs don't run on the serving machines until those machines have been attested clean. So the approach to get that property is we will have the job schedulers reach out and issue attestation challenges to the machines, and only issue jobs to those machines once the attestation check is passed. It sounds simple, that's because it is. This is one way to avoid complexities and make things simple. So the strategy, we will get measurements from a policy. The job scheduler will be informed of what the expected measurements should be. Then we will reach out to the machine and get measurements from each root of trust on it. Here we're modeling the machine as a collection of roots of trust, each of which will report measurements about the boot stack that it observed. And we'll aggregate those measurements at the job scheduler and reason about it as a whole, or we compare it to the expectations and react accordingly. Now, why not enforce the policy on machine? So I'm going to back a slide real quick. So the roots of trust are over there on the machine. Could we not just have the machine reason about itself, like I'm attested or I'm not? That would be nice, but this is what gets into trade-off between complexity and reliability. Like, it's very hard to do reliable attestation of a complex disaggregated machine, the kind that we're looking to build. So we would like to take to aggregate those measurements off machine, where we can have more flexible reaction and tailor things. Like, for example, if we observe that a certain component is a bit flaky and doesn't attest cleanly 100% of the time, we can twiddle some knobs, and we can do that without having to push software fixes out to our fleet, which takes a lot longer. Now, we're not saying that there is never a reason to push any kind of policy to the machine. There might be, for example, with PCI link encryption, ADISP, this stuff is on our minds, but for now, we are not targeting that. We're going to do the centralized enforcement, get data on reliability at scale. One note about reliability. These numbers start to get a bit interesting when you look at fleets of a certain size. So hypothetically, if you have a fleet with 1 million machines, and let's say that your attestation has a daily reliability rate of 99%, that seems cool, except that means you're gonna have 10,000 machines failing attestation every day. And even if it's 99.99, that's 100 per day. So we would target 5 nines of reliability as a bare minimum, and 6 nines would be even better. Why? Because we want to be able to turn on hard enforcement without losing a big chunk of our fleet. So that's the trade-off. If you're 99% reliable, you can either turn on attestation and lose 10,000 machines, or leave it off and do audit modes and such. And we would like to also, when failures come in, we'd like to be able to dedicate resources to investigate them and find out what's really going on. And when you have 10,000 or even 100 failures, that's too much to look at case by case. So we like to be very highly reliable so that we can really get good visibility. So that is another reason why we prefer to do enforcement off machine. All right, over to my colleague to talk about the details of the strategy.
Thank you, Jeff. All right, so as mentioned, the job scheduler needs to know two things to do an attestation: what we expect to have booted on the machine and what actually booted on the machine. So let's talk about what we expect first, which is in that attestation policy. Going back to our production network for a second, key role here is the job schedulers on the top, and we've chosen to make them among the highest available services on our network because of their importance keeping Google up and running. What does that mean? Well, it means we expect them to always be up. We expect them to only minimally depend on other services, and if they do, those other services must also be highly available. Because of this, those job schedulers can't easily reach out to query things like most other services, like, for example, the machine and software automation bubble in the bottom left. However, the serving machines that we're going to be testing here are not homogeneous. They're a kaleidoscope of build and software configurations, which can even change based on the time of day. We have constant software rollouts happening. This means that each machine's expected boot stack is going to differ somewhat, even with very similar builds. Unfortunately, the thing that knows what's actually expected on these machines is, in fact, that machine automation bubble. But that gives us an availability inversion. We previously said job schedulers can't depend on that. It's less available. So what do we do about this? Well, one option here would be to simply re-engineer more availability into the machine automation. And simply with quotes for a reason. And bringing something up to that level of availability, it's a pretty large engineering effort. It's not to be taken lightly, and maintaining something with that level of availability on our network imposes a lot of constraints on our resources. So instead, rather than ask the machine automation over the network what to expect when doing the attestation, we're going to have it pre-assemble a policy and put that on the serving machine for us to later use. After all, the job schedulers are already going to be depending on those serving machines to do the attestation. I mean, it has to reach out and get the root of trust measurements from them. So we're not adding any additional dependencies here. So whenever we install, update, or repair anything that's going to necessitate a new policy, machine automation will craft that new policy based on the expected hardware and software models in the machine. And knowing the software models alone, not enough. You need the hardware too. Google maintains both hardware and software models that it expects for each machine. But even with that, deriving the policy still has some complexity to it. For example, a machine with one NIC is going to attest differently than a machine with two NICs, even though software-wise, they might be receiving the exact same software packages. So once this policy is created, it's then sent to a trusted certificate signing service, the green bubble here, to be cryptographically signed and include revocation serial number. This signed policy is what's eventually delivered to the serving machine to be used during the attestation. And as mentioned, we chose to store the policy on the serving machine to further reduce those network dependencies. But with this approach, technically that policy could live anywhere. So what happens when we want to change what's expected on the machine? Maybe a firmware update happens, part gets swapped. That old policy is no longer valid and must be revoked. We don't want anyone rolling back, either on purpose or by accident, to the old policy. And this is done, or we do this by adding it to a certificate revocation list, which is fairly standard stuff. But again, to reduce those dependencies, the CRL is distributed as a file to each job scheduler and used when checking policy revocation. Now, by using the policy in this way, we don't have to deal with infinite duration root of trust for measurement cert management, which is especially helpful when we want to get rid of an RTM. And instead of having to manage these infinite duration RTM certs, we need to manage these policies. The RTMs have no power without the policies, which is sort of trading one problem for another, but we do find the policies to be a bit more manageable. So now here's a more accurate representation of what's happening here. Job scheduler reaches out to the serving machine to get a signed attestation policy. It validates the signature over that policy, and then checks whether or not it's been revoked. And we've architected it specifically so the job scheduler doesn't need to reach out to anything else, anything other than the serving machine to do that attestation, which is a nice availability win here. But we've yet to talk about what's actually in these policies. And here's an example of that. First, there's some general information like the machine's host name, the revocation serial number I mentioned. This includes, there's also some stuff specific to each root of trust expected in the machine, like the expected physical location, which is analogous to a PCIe or PCI address or a Redfish resource name. We also have data necessary to uniquely identify the root of trust, like a DICE-esque root cert, as well as a serial number, along with information about, animations, along with information about what to expect to have booted on the machine, like a digest of the root of trust's application firmware image, as well as the expectations about the boot measurements themselves. And those are just expectations here. They're not the actual measurements. And they could be as simple as, hey, here's the hash of the BIOS to expect. Very simple. Just compare, equal, equal, you're good. Or they could be more complex, like here's a list of acceptable hashes for that BIOS. Really, whatever you want to put in here, as long as you're willing to put some parsing logic in. And TPM quotes fit fairly naturally into this scheme by comparing the verified measurement log to these expectations. We tried really hard to make these policies very flexible and work really with any type of root of trust for measurement, TPMs, SPDM responders, Titan, whatever. And that's because we don't want to be limited to what root of trusts we're able to use in our data centers. Also, this policy logic is, it's consumed by higher level. It's logic, so it can be written in a higher level language, which in this space of boot integrity can sometimes feel like a luxury to have, but it does help make the policy more easily extensible if you want to change it or something. All right, that's the policy. But we also need the job scheduler to get the attested boot measurements from every root of trust in the machine to compare to that policy. And how do we do that? The plan here is for each root of trust to emit a signed attestation statement on demand. And the requests to get these attestation statements will include a freshness nonce to prevent replay of those measurements. And everything in between, the job scheduler and the root of trust, is treated just like an untrusted node on a network. So if a hop drops that request and the machine fails to provide a valid set of measurements, the remote attestation is going to fail. Now, our specific implementation of doing this chooses to use BMCs on the machine to route those requests to the various root of trusts and then back to the job scheduler. And one way to do this is for the BMCs to get the root of trust measurements using SPDM's get measurement command, and forward the results back to the job scheduler over Redfish, which is the machine management protocol used to interact with BMCs. Obviously, there is no law saying you must go through a BMC here. Any path to the root of trust will do. It's just BMCs are convenient for our machine design. They're already there to help manage the machines. And note, again, all the information necessary to do a local version of this attestation exists on that serving machine. But even with that, we still prefer to avoid doing it. And one reason for that is because this diagram up here, it's still a vast oversimplification of what's actually coming. Machines being built now need to route these requests through several BMCs on the machine. The hardware on them, and it depends where the root of trusts are located for that, and the hardware inside these machines can be quite complex, and that's for very valid business reasons, and we want to support that. This complexity hits on why we're opting for the remote attestation approach instead of doing it locally on boot. We want to try really hard to keep the on-machine boot complexity as simple as we can, push as much of that complexity to the control plane as possible. And we believe doing so creates a more highly available, highly reliable fleet, and also eases maintenance of some of our solutions. Okay, now we have the policy and the measurements. Next, we got to compare the two, see if the measurements actually satisfy that policy. And this is our goal here. Before issuing jobs, we want to make sure the serving machine attests clean. If the answer is no, we're going to send it to our repairs infrastructure, hopefully fix the problem. If the answer is yes, the serving machine is given details about a job to run, maybe serving one of those YouTube videos or some Gmail traffic. It's also given some short-lived task credentials that grant access to whatever data and services are needed to do that job. This is possible because all important data and services on our production network are protected by those kinds of credentials, which is how we're able to keep machines from getting access to them without a successful attestation. Key takeaway here, attestation unlocks credentials, and credentials unlock data. And at a high level, that's it. That's our solution. But this is an OCP talk, so what here's open? Some of this is custom. That's okay, totally fine. Some people might not be interested in a standard for a job scheduling infrastructure or machine automation infrastructure, but some of this is open and standardized, and we believe more should be, like how to expose the root of trust signed data to an off-machine verifier, for example. We think you should be able to buy a part from any vendor and do what we do to get the attestation signals off machine, which is why we've been working with DMTF to try to make it easier to model SPDM responders as Redfish entities and challenge those responders over Redfish to then get some trustworthy Git measurement responses back over the network. We have some industry support for this, and hopefully we'll have something published by early next year on that front. There's also a need to standardize on how to even populate SPDM measurement indices and make sense of them as a verifier. Which ones do you use? What's in them, that kind of stuff. Also, we think it would be nice to start thinking about to what degree can the policy format itself be standardized. And the open aspects of this that we're working on, be it specification proposals or reference implementations, we plan to put in a new platform integrity GitHub repo, PINT for short. There's a little bit in there now, like the SPDM plus Redfish proposal, a binary descriptor format for firmware images, and a flexible mailbox protocol. There will be more in the future, so be sure to keep an eye on that. And for the obligatory call to action, feel free to applaud if you'd like, because the talk is over. But thank you very much for giving us some of your time today. Are there any questions? Don't all stand up at once.
Hey guys, thank you for the presentation. I have a couple of questions regarding the attestation policy as well as in general around the whole process that you have for attestation. How does this model address boot integrity beyond the job is scheduled, once the job is scheduled?
So that's where we do things like, so we have a couple options there. So the very first slide we had, okay, protection, detection, recovery. So this talk was about detection, but we also are investing in protection. So making sure that, for example, RTUs, making sure that you can't flash arbitrary bad firmware after the thing's booted. There's also an attestation technique, which we did not address in this talk, about binding, sealing credentials to measurements, which is a bit of a different beast. But in that way, you can make sure that, hey, if, say, like the kernel is not what you expect, then we'll know about it.
Quick add-on there. You could also attest on every new job or something like that, or you can continuously attest every some interval to be able to keep checking the state there.
So in a different way, if I say that the model that you presented where before the job is scheduled, you attest and then don't worry about it, requires to have a robust root of trust on the system. The root of trust there needs to do everything like RTU, rec, to make sure that it is not compromised once the job is scheduled.
So this is like, gets into a bit of practicality. Like there is the ideal, and then there's the reality of we have machines where that could introduce non-trivial reliability engineering problems. So we're trying to address this in a way that gets us security wins in a reasonable time frame.
And this talk specifically was talking more about RTMs. There are also RTUs in this solution. We just anytime I mention root of trust here, assume RTM.
Yep, thank you.
I-
Yeah, okay, sorry.
I think, I'm surprised I'm not being kicked out. I think we're over on time. I guess I'll go till I'm kicked out, but assuming we have more questions, we will be in the hallway, find a room somewhere.
One question on the hierarchy. Is there a notion of hierarchical attestation at a node level, rack level?
So there could be, like, we define the unit kind of as the machine, which, you know, is in and of itself becoming a little bit of a network unto itself. But certainly this approach scales to, okay, maybe you have a collection of machines, and you have policy over that, or you have some kind of disaggregated memory, you can have policies over that too.
In this one, I feel like we treat the root of trust very similarly. We reach out to each one individually. So we don't have one root of trust answering for another root of trust, if that's what you mean by hierarchical.
Is there like a rack level RMC type of thing as well?
So we prefer to like hear directly from the roots of trust and reason about that like off machine. So the aggregation happens as we pull them off the components being attested. Like I said, like this is, you know, an active work in progress. So we'll see where things go, but that's the direction we're taking right now.
Okay, thanks.
I guess we have a couple of minutes for another one.
No.
Nope, we do not.
Cut off now.
Yep.
All right,
Talk to you
well,
afterwards.
we'll meet you in the hallway somewhere if you want to continue some discussion.